Welcome, everyone. We're going to start now the second day of the workshop. This is the morning session about quantum computing research in Italy. First part is going to end at 11:20. Then we have 15 minutes coffee break. Then we have another session ending at 12:50. Now let me introduce the first speaker of today. It's a great Italian scientist. It is Eliza Colesi from University of Bologna. She's going to talk about Bayesian adaptive techniques for quantum optimization on NISQ devices. So, Elisa, welcome. Okay. The floor is yours. Thank you for coming.
I will share the screen. Oh, sorry. I also want to see you. Do you see it? But I think you just see my empty screen, right?
Yes, we do.
Yes.
Yeah, because I don't know for what reason it closes down. Let me go back to. Sorry for that. I didn't check it.
No problem.
Okay, now it should be. Is it? You see my presentation now?
Yes, we do.
Okay, perfect. Okay. So let's first of all, let me thank the organizer for giving me the opportunity to present our research. And I also would like to acknowledge that our work is partially supported by the IFAB Foundation and the Leta Unipol Group. And also we are collaborating with Daniele and Riccardo in Cineca, and through them we are also collaborating with Pascal to implement our protocol, the one I'm going to describe you today, on their atomic platform. So actually this is the reason why we decided to work on some specific use case. And so let me present it immediately. And we're actually working on a combinatorial problem on a graph, which is called the Maximal Independent Set, which has a lot of interesting application to also real life situations. So the MISQ problem consists of finding in a graph with some vertices and links, the maximum number of vertices which are not connected to other vertices in the same subset. Okay, so just an example, I'm showing you a very simple graph, but not so trivial to implement, of 6 vertices. Each vertex becomes a qubit. And the problem of finding the maximal independent set can be put as in a quantum setting to find the ground state of Hamiltonian, which is the one which is written here. And I also give you the simple solution that can find by hand on this example. And the idea is that on the atomic platform developed based on Rydberg atoms developed by Pascal, is optimal to encode the topology of the graph thanks to the physical process which is called the Rydberg blockade, in such a way that atoms which are distance between each other by a distance bigger than a given radius, Rydberg radius, are actually essentially not interacting, and therefore they are not linked in the graph we are considering. And then what we are trying to do is to look for the solution of this problem by assuming only global pulses. So we will work on the Hamiltonian of the Pascal platform that I think was shown to you yesterday, by using only global pulses, or Rabi and the tuning pulses on our Hamiltonian. And this is just so we are trying to implement this in an analog setting, not just a digital one. Okay, so what we are going to use is a hybrid protocol, classical quantum, which is a quantum approximate optimization algorithm. And the idea here is that in order to find the minimum of our Hamiltonian, which corresponds to a sort of a cost over objective function, we're using a quantum circuit first, which will take some prepared state and will evolve it through a parameterized quantum circuit. And then we will make some quantum measurement to average our Hamiltonian to get the objective function here. And then we will use a classical computer, a classical optimization algorithm to get the best value of the parameters. And then we go on with in a loop of this procedure, quantum classical, and so on, until we reach convergence to some optimal values of our parameters. So this is what the essential, in very few words, quantum approximate optimization algorithm does. Clearly, all these steps have some theoretical issues to be kept under control. First of all, convergence, but I'm not going to concentrate on that. And also, let me stress that all these steps might become quite resource demanding if you really want to achieve a good accuracy. And clearly, this is a problem if you want to work to implement our protocol on a real NISQ device. So let me describe a little better how we implement this algorithm on the Pascal setting. We are using by now the Pulsar emulator, which is given by, that one can use directly on the internet platform of Pascal. So, in order to implement the QA algorithm, you might know that the QA algorithm is based on a series of steps that's called, let's suppose they are P of them, and each step is actually organizing a two-step evolution by means of two Hamiltonians, one with an angle that we call beta and the other one with an angle that we call gamma. And the two Hamiltonians do not commute with each other, and the Hamiltonians that we are using in our problem, the ones that are given here. So essentially we're using a laser signal that are the one that you can see in a small example with P equal 3 with 3 steps in the picture below in this graph. So for a total time of about 2 microseconds. And so that we are able to evolve in a subsequent way through the first Hamiltonian that we call HM, and then through the Hamiltonian HC, and so on, with different times, beta 1, gamma 1, beta 2, gamma 2, and so on. And then the idea will be that at the end of this evolution, we will have spanned parametrically our Hilbert space. And therefore, we want then to take a measurement in order to calculate our objective function C, that the one that I wrote before with a penalty P here, which is that we set up to 2. It's enough to set it up to 2. So that I remind you that the objective function is such that the ground state of this function is actually our solution. So in a real computer, the quantum measurements that we have to take in order to evaluate C are actually destructive. So we actually, in order to calculate the average value of C over the final state that we have prepared with our parameterized quantum circuit, have to be repeated many times. We call this number n shot, in order to end up with a histogram, which looks something like the one that I've shown as an example on the left side of the slide, out of which one can get the average value of C. So this means that from if you really want to perform this computation in a real computer, we need to repeat the quantum circuit many times, exactly n shot times, in order to get a good estimate of the average of the objective function. So what I really am going to concentrate among the many problems that on a NISQ devices we might have is how we can control this number of times we have to run the circuit, so this number n shot, and how you can use a Bayesian approach in order to reduce such a number. Okay, so indeed our idea is to use a Bayesian inference to reduce exactly this number of experimental acquisition that we need to make in order to calculate the average of the cost function. In this Bayesian approach, the idea, I'm not going to describe it in detail, the mathematics which is behind this approach, but the idea that the optimization problem shifts from finding the minimum in the energy landscape of the Hamiltonian to the maximum in what one calls the acquisition function. Let me stress that in all these problems, the energy landscape is very rough. Okay, it has a lot of maxima and minima, and can vary a lot also as we change, for example, the depth of the QA. So this Bayesian inference allows us to simplify the problem quite a lot. And the idea is that with this inference, we're able to give the best estimate where to go to look for the new measurement. So the idea is it is very easy, as simplified in these two pictures, that if you want to estimate some objective function, which is the dashed line in the picture, and we just know, for example, the function in 2 points, because we have already taken 2 measurements, this Bayesian inference procedure will allow us to find through this acquisition function what is the best point where to look for, where to make the next measurement. So we will select the new measurement point using this Bayesian inference protocol. There are several things to take into account while doing so, like the correlation kernel, which contains 2 parameters, the constant and the correlation length, that has somehow to be fixed consistently with the data. I'm just mentioning them because I'm going to show you some graph later on. And also we have some convergence parameters. Usually the standard deviation for energy is one which is used. In order to have a good convergence, we needed also to add what we call an average square distance in the genetic algorithm, which is a differential evolution algorithm that we use in order to obtain the maximum of the acquisition function. But I cannot, of course, enter in the detail. If you have questions, I can answer later on. So these are just as a summary, the result of our of all the parameters you need to keep under control in our protocol. Okay, so we have the angles and the number of shots in our quantum circuit. We have the data of our QA protocol, the depth, the number of points we start with, which is of order 20, and then the number of steps we make in order to get the minimum. And then we have all the data of the parameters that are characterizing our genetic algorithm. And this is, for example, the kind of result we can get for some instances of the circuit. The quantum part is done with the pulsar emulator, and then we run this data. Actually, have been run just on a personal computer, just to give you some ideas. I just highlighted a few points in which there might be problems. Okay, for example, you can find that there are some situations like the p equals 3 case here, so the QA p equals 3 case, in which we start finding some plateaus in the fidelity and in the energy, which correspond to the fact that numerically there are some problems because the correlation length of the kernel goes to 0, and then we are not able to reach the required accuracy in the calculation. We are right now starting to take into account these situations, these instances. But of course, I have no time to go into the details of all this data from which one can see many interesting things. Let me just try to give you a summary of what we can find. So this, for example, you can summarize our result in the calculation of the fidelity, which is measuring how much the ground state, the final state that we get with our algorithm coincides with the true ground state of the Hamiltonian that we are able to calculate with exact techniques for this simple problem, as well as the energy, okay, the convergence of the energy. So as you can see here, we get a worsening of our data starting from p equals 3, which depends on that problem that I was mentioning before. But as you can see, in general, if you go, for example, from P1 to 2, we get quite a high fidelity of the order of 3/4, and a good improvement about the value of the energy. And Okay, even if I'd like to make a comment about the problem that we might encounter here, that if you if you go on with the depth of the QA, we sometimes run into problems because we do not see a monotonically uniform convergence. But let me stress, however, that we checked the solution that we find, which is, so we check the histogram of all the possible solutions that we found with our protocol. And we see that, and what we calculate here is actually that we see in the last column here is the ratio of the probability to find the exact solution with respect to the probability of finding the second most probable state. Okay, so this second peak here, which is a wrong case. And in anyhow, even when the situation is not so good, like p equals 3 here, or p equals 4, you see that the ratio is quite high. So this is telling us even if our final state has not such a high overlap with the true ground state, still the other possible state appear with a very low probability, so the chance to get the right solution is really, really high. Okay. And this is a final graph I would like to show, just to give you an idea of the total time for the simulation to take place. As you can see, as we expected, it essentially grows linearly with the depth of our QA circuit. Let me stress that these graphs are very coarse in the sense that we have not optimized yet our software. And also we have not tried to, we are by now actually trying to parallelize it and to be able to work it on faster computers. So up to now, as I said, we have been doing just quantum simulation on the pulsar emulator by Pascal with the addition of classical optimization procedure on just a standard computer. And by now we are working on optimizing our software in order to run it on a better computer. We are going to use Cineca's computers. And we are also performing a benchmark of our Bayesian approach with respect to other classical optimization strategies to see if indeed this Bayesian approach allows us to get faster and better results. Let me then, as a last comment, stress that we are running simulation on pulsar also by adding noise. I didn't have time to talk about that, because our final goal will be then to try to run our algorithm on the real atomic platform, possibly in the first month after, in the new year. I think that's all I wanted to say. I thank you again for this opportunity.
Thank you so much. Let me check if there is any questions in the chat, but I do have one. As you had no time to talk about the noise, let me ask about this very last point you commented. So how aggressive is the model of noise in the simulations? What is the concept of the noise implemented?
Okay, I mean the Pascal has already implemented the emulator for the noise in their system, which includes different kinds of noise. I mean state preparation, measurements, errors, stability of the signal, and so on. So we have just started to run. I mean the emulation with by taking into account all the different kinds of noise in order to be prepared to can happen when you go to the real computer, the real platform. Okay, this is I don't have actually, unfortunately, graphs to show you because we are just starting now to do so. But on the emulator, in the emulator, there are all the protocols to take care of that.
Thank you so much. Okay, I think there is no time for additional questions. Thank you for your excellent talk.
Thank you to you.